logarithms which have a base of 10. Any positive number other than 1 can be used as a base for a logarithm. However, most oftenly in the real world we use common logarithms, a base of 10, or natural logarithms, a base of the number e. It's a letter, but it's a number. Like the number pi is 3.14. Everybody's used to that number. The Greek symbol pi represents the number 3.14. Well, a lowercase e represents the number 2.71828, and it goes on and on and on. Matter of fact, your calculator, your graphing calculator, above, in the very first column, above the key that says ln, a little ln, above that is an e to the x key. That's a key that will let you get e to some power if you'd like to do that. But anyway, we're going to be talking about natural logarithms. Natural logarithms do not have a base of 10. They have a base of the number e. Now, what I'd like you to do is with your calculator, and I'm not going to be able to demonstrate this, but first, a base of 10, I want you to find the log of 20. Now, the way you do that is in the first column, you hit the log key. It will open parentheses, you type in a 20, and you close it. That's it. And you're going to get an answer of 1.30, and I'm sorry, this is approximately, this is not exactly that. It found for you the log of 20 to be 1.3 because I want you to remember there's an understood base of 10 here that I didn't write, and what the calculator needed to do is it needed to go and find 10 raised to what power, and it's 1.3, would give you 20. You can check this out now. Go 10 caret 1.3 and see if that's approximately equal to 20. That's what the calculator did for you. When you asked it to find the log of 20, it said, okay, 10 to what power is 20? That's what it did. Well, we're studying in this section the natural log. That's what we call it. Sometimes we call it the ln. Literally, ln. Find the natural log of 20. Well, in this case, I'm asking the calculator to take a base of e and raise it to some power here to get 20. Well, that power that it's going to raise it to, or if you hit the ln key, it'll open parentheses, you type in the 20, it'll close it. You should get 2.995, or I'm going to say approximately 3. And let's just check this. What I want to know is e to the third power, this to the exponential power, is that equal to 20? And what you would do on your calculator now is you'd have to hit the second key, probably in yellow, and then you'd hit that ln key because above it is e to the x power. So second ln gives you e to the x, and then you need to type in a 3 and hit enter. I'm going to use this symbol. Hit enter, and you should get approximately 20 for that. Again, this gives you e to the third power, approximately equal to 20, and I just wanted to check this to see if that was the case. Early on in this section, in the homework, all we do is ask you to use your calculator. Find the natural log of 20. And when we ask you to do that, we're not going to tend to put this e here. We're just going to say, find ln of 20, and you'll just hit the ln key, it'll open parentheses, put the 20 in, close, get this. And if you wanted to, you could check it by saying to yourself, does e to the third power give me approximately 20? Also in this section, we'll ask you to find e to some power. So just get some practice using this second ln key. Use that e to the x power key as well. Very good. I'm going to take a break here and we'll go on to the next topic. Okay, similar problems to what we've just done, but now I'd like to suggest to you or make you recognize that we are not able to, at this point, we are not able to take the log of a number where the base is something other than 10 or e. Because you have in the first column of your calculator a log key, log, that means a common logarithm, base 10, and you have right below that an ln key, which means a base of e. But you don't have a key that allows you to take the log of 7 when the base is 2. So we're going to talk about that now, but just to kind of keep you practicing this, the log of 732 should be between 2 and 3 because the log of 100 is 2, the log of 1,000 is 3, and that turns out to be 2.86. If you hit the ln key to find the natural log of 91, that you should get 4.51. And now I'm going to tell you that there is a theorem that allows you to find the log of any number where the base is anything And I'm going to write the theorem over here, and then we'll practice it right here. The theorem says, if I want to take the log of a number where I have some base, that I can take the log of this value right here, m, and divide it by the log of this value right here, the base, and I get to choose any base I want to use. I've just put in there little a's in case you can't see that. The log of m where the base is a divided by the log of b where the base is a. Again, I get to choose the base. Again, this m and this b go here and here. So in this problem right here, what I'm telling you is that you can take the log of 7 and divide it by the log of 2. Pick any base under the sun that you want to use, but in my opinion, I'd pick one that your graphing calculator can do for you. So personally, I'd pick a 10 for my base. I'd use common logs. And so all I'm asking you to do, now please remember, when I want to know what the log of 7 is, let's write this down here, where the base is 2, that's what I'm looking for. If I put that in exponential form, I'm asking you to take 2 and raise it to some power and make it equal 7. Well, I know that 2 to the third power is 8, and 2 to the second power is 4. So I know my answer here should be between 2 and 3. Again, 2 squared is 4, 2 cubed is 8, and this is between 4 and 8, so my answer should be between 2 and 3. Now what I need you to do, I'm going to get some of the clutter off here. I need you to take your graphing calculator, and I need you to be very careful about this. I think I'm going to handwrite what you'll type in. You're going to hit the log key, it's going to open parentheses, you put in the 7, close parentheses. Then would you hit the divided by key? It will show that. Then would you hit the log key? It will open parentheses. Would you put the 2 in? Would you close parentheses? And then would you hit the enter button? And when you do that, you should get a number between 2 and 3. And as a matter of fact, I believe that turns out to be 2.81. The common mistake that people make in typing this into the calculator and using the change of base theorem is they type in this. Notice the difference. People make a mistake, and when it opens parentheses, they type in 7 divided by 2. That's not what this says. This says take the log of 7 and divide it by the log of 2, not the log of 7/2. So you got to take the log of 7, close parentheses, divided by the log of 2, close parentheses, or it will not do this calculation correctly. Now, would you just go back and check this? If the answer to this problem is indeed, I'm going to get rid of this so you can, if it is really 2.81, would you check this by taking 2 and raising it to the 2.81 power? So 2 caret on your calculator, 2.81, hit enter, and you should get approximately the number 7. Now, I didn't need to use, I'm going to get rid of some of this, I didn't have to use, for this very problem, common logarithms. I could have chosen to use natural logarithms. I could have taken the natural log of 7 divided by the natural log of 2, because the change of base formula says use whatever base you'd like. No, it's not really necessary for me to do that, but I could have, and I would have gotten the same answer. If you would type into your calculator natural log 7, close parentheses, hit the divided by key, natural log, it'll open parentheses, put the 2, and then hit enter, you should get the same answer we just got a minute ago, which was 2.81. And that helps to prove the change of base formula. Use any base you'd like, but I can't do this without the change of base formula. It's a very difficult problem to do. One more example, and it doesn't change at all. So if I asked you to take the log of 9, where the base is 4, I'm making this up as you can tell, I want you to take the log of 4 and divide that by, the log of 9, and divide that by the log of 4, clean that up a little bit, and divide that by the log of 4. You pick the base, but I'm inclined to pick a base of 10. Now it happens that since I just made this problem up, I haven't done this problem yet, so I'm going to do it real quickly. I'm going to hit the log key, and I'm going to type in a 9, close parentheses, divided by, hit the log key, it'll open, put the 4 in, close parentheses, and I get an answer for this of 1.58. That means, again, here's my answer. That means I want to take the number 4 and raise it to the 1.58 power to get approximately a 9. This is my check. I want to see if that works out. The change of base formula is awesome because now I don't have to just work with logarithms with base 10 and base e. I can work with logarithms of any base. The last objective in the study of natural logarithms is to look at the graphs of exponential functions involving e as a base and the graphs of logarithmic functions involving e as a base, or natural logs. I'm not going to spend any time here because we did a bunch with that in the introduction to this chapter, graphing exponential and logarithmic functions. All I'm going to say to you is that if I were to ask you to graph the function e to the x power, that you just need to create a table, pick some values for x to put in there, and use your calculator, and right here e to the 0 power is equal to 1, and e to the first power is 2.71 because that's the definition of e. And again, I haven't done this on my notes here. E to the second would be something, and e to the third, and you get a graph that looks like this, an exponential curve. If you were to graph the reciprocal function of e to the x power, you'd be graphing the natural log of x, and that's going to look like this. And these two curves, since they are inverses, are going to be reflections over, here's the e to the x, here's the natural log, over the line y is equal to x. And so that's all you'd be expected to do as a closing to this section of natural logarithms.